Yo, what's up, everybody? Welcome back. Today we are working on implementing USB on my custom controller firmware. So, context: we're making a Xbox controller from scratch. This all started because I want to shit talk children in Fortnite, but I don't want them to hear when I get angry and I punch my desk, right? So I want to push the talk button, and the controller I have, he has paddles, which is great. I can use one of the paddles as push to talk, but I can't bind them to like keyboard keys. I can only bind them to other controller keys. And I need all the controller keys to play Fortnite. They're busy. I'm working with them. And so, the obvious fix to that problem is to make our own controller from scratch. So, this is where we're at right now. We have, some hardware. We've got a PCB, not shown here, that's like almost ready to go. The intent here is to kind of follow in the footsteps of, the leaders of open source controller. Right? So if we look at this guy, what they've done is they have basically just taken a Raspberry Pi Pico, like a well-known microcontroller, and just slap that shit on the back of your PCB, right? So we're following their footsteps. Really, the core of this guy is actually this system on a chip right here, the RP2040. Probably if we were willing to like solder this thing on ourselves, then we could probably save like $6 or something. But fuck it, we'll do this because they're doing it and it looks kind of sick. Repairability there is like really nice and easy, and $7 for the chip for the microcontroller is not that bad. So the plan is we'll use this guy. We'll plug a USB port. We'll plug a USB cable in here. Boom, got a controller. Problem: we have to fucking talk USB, right? So, that's the plan for today. Is try to figure that out. So we've taken a couple runs at this. We've kind of like over the past few weeks, we've kind of hit like some like prereqs a couple times. So some related work here is that we have kind of written a USB device driver for a Xbox controller on Linux just to kind of see what is this thing like supposed to talk. So we've kind of like got that in our head a little bit. It was relatively high level by some definition of high level, right? Obviously, from like the context of like web dev programmer, very low level. From the context of like I'm wiggling bits on wire, pretty high level. And then we also found that the USB clock in this guy has to run at 48 megahertz. We hadn't initialized those clocks yet, and that actually took like a little bit of effort. So we have done this before, but otherwise, we got a fair amount of work to do. So I don't know. The plan is like try to turn on the USB controller, prove that we get some data. The Linux box is going to ask us a little bit of like metadata about our device, so try to provide that in some way, and then presumably we're not going to be correct, and so we're going to have to like have some other things to clean up there, but I don't know what. Yeah, that's the plan. For a little extra context, we are intentionally sidestepping the Raspberry Pi Pico SDK because we are masochists. But we're writing our whole thing in Zig from scratch. So if you were to buy a Raspberry Pi Pico and put it on your desk and use it, you would have a much easier time at this than we are. But we like understanding kind of like the really nitty gritty of stuff around here. So we figure doing it this way means that we'll get a little bit of a better understanding of the hardware. Okay. So USB. The fuck is USB? We'll draw a little picture, a nice little picture for us. So we got our little Xbox controller. Wow. He's got, a D-pad and some face buttons and a couple sticks, right? Wow. He's got, he's plugged in through USB to some USB controller, right? So you can imagine this as like a PCI card in your computer. Technically, you guys probably don't have like this type of PCI card, but I think that the controller is still on the PCI bus, just kind of like embedded somewhere on your motherboard, maybe even in like within the south bridge of your CPU. I don't quite remember, but I do think that these things are always exposed as a PCI device from the perspective of your computer software. This guy talks over PCI, I guess, through these pins. They go over to the CPU, right? And this guy, you write some software to do some stuff. Then, you have like kernel space, you got like Linux here, in my context, is going to do a bunch of work for you. And then you have, our program who reads some inputs, right? So we're kind of working here, right? So we don't really have to worry too much about like all of this stuff, but it is kind of nice to understand that this is the way things are hooked up for when we're debugging. So we're really mostly worried, like technically you would think that we're worried about like the stuff that goes over this wire, right? But kind of because of the fact that like the Linux, like from the CPU's perspective, he's talking to this guy. It actually turns out that our hardware interface is kind of going to more mirror this transaction than like this transaction, right? Because like we are on our side within our controller. How do you do this? You draw like a little magnifying glass and then you like expand. In here, right? We have on our side, a CPU, and he talks to our USB controller as well, right? And then he sends stuff over the wire. So since we are talking this interface and this interface mirrors this interface, like we don't really have to worry too much about like the individual bits on the wire. Hand wavy. That's my understanding right now. Could be wrong. Background, a little bit of background for like USB. So they have 4 data lines. I know I said we are 4 lines. I know I said we just don't care, but knowing this is probably useful in some way, we got like ground, ground, power, and then plus and minus here, where this is basically saying like, if you're sending a 1, the difference between these is going to be big, and if you're sending a 0, difference between these 2 lines going to be kind of small. There's like kind of like known packet formats that each of these cards is going to be sending and receiving and looking for. I can't really remember the details here. I think it's something like you have like packet type and address and endpoint, I think, in here. And then data, something along those lines. Not too important, but like basically there are like packets that come in as sequences of data, and those have like packet types and data types and all that jazz, addresses, endpoints. That's kind of like the big 3. So when we plug this guy in, what we should expect is to kind of go through this USB state machine from the USB 2.0 specification. We plug our guy in. He like yanks a line low. I think that these, I remember correctly, some of these pins are like kind of like automatically pulled high, and when we plug our guy in, he like pulls them low, and so then the controller goes, oh fuck, someone's connected, someone's plugged in, shit, time to do some work. So then we go from like attached state to powered state. The bus issues some sort of reset call. I don't really know what that means, but like he resets the device, we go into default state. In default state, the device is like just address 0. Because like, I guess what we didn't talk about here is that even though the controller is going to have like multiple USB ports on it, right? You plug in multiple devices here. All of these are just going to like end up on the same lines to some chip, right? Because like this chip isn't going to have like pins set up for every single device that it can plug into the whole bus. It's kind of like, okay, I'll have one set of pins that I talk to, and then like I'll talk to one guy at a time type shit. So he gets plugged in, he has address 0, the computer goes, hey, or maybe like the hub, we're not really sure yet. Somebody says, yo, you think you're guy 0? Could you just be like guy 13 for me really quick? And then he's like, sure. So then he gets an address, and then we like config, maybe some devices have like multiple things they could be, right? Maybe I'm like, I don't know. I don't have any good examples. Maybe I'm like an Xbox controller, but like I also want to be like a Switch controller, right? And so like maybe we have configurations for both of those outputs, and like the guy picks one. And then we can talk to him. So we're kind of hoping to like see some evidence of this flow on our device. So don't really know how it's going to work. I've kind of popped open Wireshark here, and I have kind of captured a set of stuff happening when I plug in my Xbox, like a real Xbox controller here. And it looks like we kind of like talk to the USB bus a little bit, the USB hub a little bit. Eventually we see down here that we start talking to a device at 113. So this is the Xbox controller itself. So this is probably once he's got the address set, we've probably run through, you know, we see some evidence here of like port reset and shit. So probably we've kind of like gone through all of this stuff. He's got an address, and then here we see like evidence of him requesting configurations and data and stuff, and eventually calling set configuration before doing some communication. I do think some packets are handled before it gets where Wireshark can see it. I agree. I think that's likely. USB keyboards often pretend to be multiple keyboards at once because USB HID supports only so many simultaneous keys pressed on a keyboard. That's pretty fucking funny. that's a good little piece of info. So I guess, you know, step one is try to like see any evidence of anything like this happening when we turn on our guy. Right? So let's do that. So when we like work with this guy, our Raspberry Pi 2040 RP2040. Where is our picture? We need our picture. Right? So he's got like a USB controller on him, and this USB controller is kind of just sitting there on like the memory bus, right? So we just like write to some memory addresses, and the USB controller goes like, "Oh shit, he talking to me, bro," and he starts like doing some stuff, right? But before we do that, we have to turn him on. So I think that like kind of by default, all of the like peripherals inside of our device are off, and we have to turn them on. That's been the way it's worked for everything else so far. So let's look to see if we can find some evidence of that. If I remember correctly, everything is kind of, we have like one global like reset my shit thing that we can talk to. There's USB control is probably the guy. ADC, bus control, I2C, IO, yeah, surely. We've probably already turned on the PLL for USB, so surely it's this thing, right? Surely. Let's try that. So let's add that field to our definition of shit we care about, and we can maybe do some USB initialization here. I don't really know where this is gonna go. Let's just kind of slap it down here. Init USB. And we're going to do something like take the reset register and modify him to do like USB control on, or is it 0? Reset it's 1. On reset it's 1, so we want to put it to 0. Take it out of reset. Does that file? It does. Okay. So the question is do we actually need to do anything other than that to see evidence of something happening in like the world? That would be kind of like an interesting thing to look at. So let's just put a while true here, just so that, you know, we don't jump into the rest of our program. And let's just kind of see if something happens here. So let's go to Wireshark, hit start, and then run this guy again. Okay, so I don't think that we're seeing anything that interesting. 1.4.3 here is the... Oh, this is the Raspberry Pi debug thing, so let's just filter that out as well. Okay, so clearly there's more work to do than just turning that thing on. I guess we should probably look for some proof that it's on at all. So maybe we should try to talk to the USB controller and see if it responds in ways that we expect. So we could look in here for like USB, and let's just kind of like see if he's got some registers that we can like talk to. Let's look at like USB power. Everything's 0 here, so that's not really that interesting. I'm looking for something that like will tell us. Maybe we like ask if when it turns on, it like has something other than zeros in its default state, so that we could like see some evidence of the thing being on. Here, what's this? USB PHY trim register. So we're looking for 1Fs on this guy. Let's look at this. Let's look at this guy. So we're gonna be like somewhere. We're gonna have like our USB controller. And he's gonna have some base address at here. Okay. And then that whatever fucking register we just saw that had those 1Fs, USB something trim, trim phi. Did I miss it? This one. So this is at address 84 offset. So trim phi is probably a volatile U32 at base plus this, and we have to do a pointer from int here. And then can we just like trim USB trim phi? Can we just read this thing? And then breakpoint, and then just take a look at see what it is. Huge. That's huge for us. Mega big for us. We got some 1Fs. So that means that the controller is on. And presumably we have to like do some stuff to get it to, you know, initialize as a USB device versus USB host. There is an example of using this thing with the Raspberry Pi Pico SDK. Now, we're not really trying to use the SDK, but we can see what they're doing in there as a way to like figure out what we're supposed to do. So in here, you know, they do their USB device in it. They pull this guy out of reset, hype. They clear out his old memory. I don't give a shit about this. They enable interrupts. I don't give a fuck about that. I'm more interested in like, how do we set this guy up as a host? Here, or as a device. Here, probably this, right? Enable the USB controller in device mode. Here they force VBus to text a device thinks it's plugged into a host. I feel like that should happen automatically. I'm kind of curious to see where that goes. And then they also say, please use the onboard PHY, which is probably something we should do. So let's, because I think that there's like a way for you to plug in an external PHY to this guy if you wanted, like the like actual connector on the end, but we're not doing that, so we don't have to. So let's say use normal PHY, and then init device mode. These are probably the two things that we want to be doing here. And so this is the use normal PHY is muxing register. We want mux to PHY and plus softcon is what he set. I don't really know why. We'll kind of come back to that and try to understand that. And then here for this guy, they say main control is set to main control, like controller and bits, whatever the fuck that means. Whatever the fuck that means. Okay, so let's try to find this like muxing register. I would like to zoom in, please. Thank you. And see what the fuck is going on there. USB muxing here. So where to connect the USB controller? To digital pad, to XFi, to PHY, softcon. Okay, I don't know really what these things mean. I would be interested to look at like USB muxing. Is that like referenced anywhere else here? Maybe in the USB chapter, they talk about like external PHYs or something. No, that's power stuff. What about here? Endpoint control register, blah, blah, blah. What, can I look for like PHY here? USB PHY provides the electrical interface between the data pins and the digital logic. USB PHY uses this stuff, has built-in resist, pull up, pull down. None of this is really talking about the fact that we could swap it out. There's an integrated USB PHY which interfaces with the USB controller. Yeah, I mean, it's not really saying a lot about the fact that you could use someone else, but like the implication here is that you can. So it could also be that they're like using some sort of like built-in or some like pre-packaged USB controller, and like even if in this hardware configuration, this doesn't make sense. Maybe in other situations it does. So I guess we'll just do what they do, and I'm not going to question it too much. But maybe that's like a future thing to understand. So here we're probably going to do something like USB muxing. We're gonna. We have a way to like set all registers or something? I think it's modify all, like this. And then here, we should get like autocomplete on all of our fields once we set this thing up. So we go into our like code generator here, and we'll go USB muxing register is a guy that has some fields. We got softcon at bit 3. We got 2 digital pad at bit 2. We got 2 phi at bit 1. And we got 2 phi at bit 0. And so if we build this guy, he's going to be mad because muxing doesn't exist, but we'll fix that. We should be able to be like muxing is this piece of thing, this code that we just generated, which is registers USB muxing initialized with base plus whatever the offset of this guy is, 74. And now this should give us autocomplete on what we need. So softcon is, we set softcon and 2 phi, right? Is what they said in the other guy. So that means 2 digital pad is off. And 2 phi is also off. Okay? And then they turned on the main control register, they turned this motherfucker on. So what's going on here? Main control register. Enable controller. In which mode? Reduce timings for simulation. And then everything else is reserved. So let's define this register as well. USB main control. We got some fields. Looks like they're all 1-bit fields. So we got sim timing at bit 31. We got host and device. Whoa. I think that I kind of want this to be a enum. I think. How do we do enums again? We just write a type field here. So we say we're going to define an enum that's called host and device. Okay. And this thing is at bit 1. And then we're going to have the other thing, which is controller en at bit 0. So now we have to define that host and device guy. So we're going to say we have some enums here to define. And it's host and device. He is a single bit. And fields are device is 0. And host is 1. So that should give us some like nice names to use later. Then this seems to be valid JSON. He's mad. What's he mad about? 612, column 24. Forgot a comma. True. That compiles, and so we can go back here and try to use this guy. So it should be... we need to define that register, I guess. So we have main control initialized with base plus whatever the offset of this guy is, 40x. And we should be able to just be like USB main control modify all parameters. We want to initialize everything kind of, which be sim timing. We want that off. We want hosts and device is equal to device mode. And we want controller en is equal to 1. Right? Seems good? Seems good? So Let's see if that gives us any evidence of anything happening. I don't see any evidence of this guy noticing anything being plugged in, right? So rerun this guy. I guess maybe we want to intentionally reset him to like get this shit back up. So reset, modify USB control, put him into reset, then take him out of reset and then wait for it to get finished. Maybe we like do wait for, you know, a couple milliseconds. On both sides here, just to like kind of give it time to like finish resetting. Weirdly, there's like a better way to do that, but like fuck it for now. And like, now do we see anything? No. Right, so that in and of itself, just turning the controller on is not enough. Also, we should probably prove to ourselves that it is on. I guess they did this like force VBus detect thing, which is interesting. Oh, and then present full device speed by enabling pull-up resistors. Interesting. So yeah, how does like connection get detected is like a thing that we should think about. Okay, can we read this for maybe a USB controller can be connected up to GPIO pins for the purpose of VBus control. Use enable VBus in host mode. VBus detect used to detect that VBus is present in device mode. Can also raise a VBus detect interrupt. Okay. So this is interesting. So if we turn on the VBus detect interrupt, I wonder if we can like get this to trigger so that he knows he's plugged in. I don't really fully understand right now, like, the connection, like, handshake, if that makes sense. Like, what do we have to do before the USB hub, like, notices that we exist? Is something that's, like, really not clear to me. Line state detection. Line state detection module has several state machines. Oh, this is probably more for like data stuff, actually. Serial engine, yeah. I know I've seen something about inrush current being used to detect device attach. Yeah, that doesn't sound unfamiliar. Uh-oh. I don't think we've done this. Within the USB peripheral, certain host and device controller events cross from USB to sys. Many of these signals do not have appropriate synchronization methods. Oh, sure. Sure. We should put a note for that, but I don't think that should cause the problems that we're seeing now. But fix me clock sys should be running at 48 megahertz at least. It's not. But I don't think that's that's related to the fact that like it's not detecting us right now. That should be later when we're trying to like communicate stuff. We'll fall the fuck over. Okay. Well, I mean, they're doing other things in here. Like VBus detect here is kind of interesting. They enable interrupts. Okay. So this is interesting, this like power stuff. This is not that interesting, like interrupts. I don't really care right now. And then this is interesting as well. This like presenting a full speed device. So can we go back? Take a little peek at this. So this is the SIE register, I think they said. Where's our like register list? here. So, okay. Okay. So here they have control pull up enable bits. Pull preamble, no. Device, enable pull up resistor. Host, enable pull down resistor. So this, we probably have to do this to like get it to say, yo, you're a fucking, like, this must be how it detects. And if we don't have the pull up resistor turned on, then it won't ever see us plug in. This seems most likely to be it to me. We should get into a shell that has what's the word? Language servers for C enabled. So we can figure out what those things are. I'm pretty sure that's what we're saying. It must be this. It has to be. Examples, USB device low level. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18. Is that right? 0, 1, 2, 3. Oh no, minus 2. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Hold on. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 is set to a 1. Yes, that's this. Okay, that makes sense. So this is the SIE control. And I guess we'll kind of leave everything the way it was and just set the pull up enable to 1. And so that means that we need to go into registers and define SIE control. And we'll say we don't give a fuck about anything in the world right now other than pull up enable. And this is bit 16. Okay. Then here we need to define the SIE control register, which is at 04C. LSP restart. Okay. Okay, that's a really good sign. We're seeing, like, for the first time, this guy's, like, spamming some shit, right? So, restart, run this again, boom, shit's happening, and he's, like, mad because he's, like, resetting this guy nonstop, and it's, like, not responding the way he wants. But I think that's kind of some indication that this guy is on, right? And now we have to find some way to get some data out of this thing, right? So almost certainly the USB hub here is starting to like say some shit to us and we're just not answering maybe, right? He's calling, you know, get descriptor device request and we're like, his response is like, I think I saw, you know, protocol error, right? We're just like not fucking answering good. Right? So presumably there's some way for us to answer good. Right? Presumably. So I assume that this is probably related to endpoint setup. Or maybe just like interrupts, right? Here I think that we saw that there are interrupts for when a buffer is done, bus is reset, and then also per endpoint 0 transaction. So something that we haven't really talked about right yet, I think, is that USB devices have several endpoints, which are just basically like things to talk to. They're kind of like modeled as like buffers, right? So like there's going to be an interrupt buffer that has the mouse position type shit, right? And you just like pull that thing and your USB device goes like, oh, yep, here's that memory. Boom, here you go. Boom, boom, boom. And so like you might have different endpoints for different things that you want to talk to. So like maybe on the controller you have one endpoint to control the LEDs and like one to read button presses type shit. And so there's also the default control endpoint, endpoint 0, that has a bunch of things that are expected of it. So it's likely here that we should be seeing some sort of like we should be seeing some sort of endpoint 0 requests. And this is kind of indicating that there are interrupts you can enable when endpoint 0 is hit. So this guy is saying, I want endpoint 0 interrupt 1 buffer bits, probably. So this is at like 1 to 8, 8, 16, 24, 28, 29, 30. So I think this is bit 29 is set on SIE control. I think that's what that's saying. So that's this. Set bit in buff status for every buffer completed on EP0. That doesn't really sound like setting it like an interrupt that is going to that doesn't sound like it's going to trigger an interrupt for me. I don't think. While that is interesting. I mean, it says enable an interrupt. And it says int in the thing. So maybe if you have buff status, maybe buff status triggers interrupts. That's maybe, possible. A bit set here indicates that the buffer is completed on the endpoint. If the buffer interrupt is enabled, it is possible for 2 buffers to be completed. Okay. Buffer status register. A bit here set indicates that the buffer is going to be completed on the endpoint. It is possible for 2 buffers to be completed. Okay, so here they're basically saying, like, when I see something, this will get set. Okay. And then presumably we have to do something with that. Can we look at like the docs in here might say something about interrupts in general, which might be interesting to read? Interrupt. Memory layout is different, blah, blah, blah. Host controller can pull up to 15 interrupt endpoints. Oh, interrupts are, interrupt endpoints is like a type of data transfer in USB, so that's an overloaded term here. Oh, here we go. Okay, this is interesting. So, endpoint control register is used to configure an endpoint. It contains the endpoint type, base address of its data buffer, interrupt events that the endpoint should trigger. A device must support endpoint 0 so it can reply to setup packets and be enumerated. Okay, as a result, there is no endpoint control register for EP0. Its buffers begin at this address. All other endpoints can have single or dual buffers and are mapped at the base address programmed. As EP0 has no endpoint control register, the interrupt enable controls for EP0 come from SIE control. These guys. Haha! Okay, so here he's giving us a little bit more specific detail about this thing. Enable interrupt for every transferred buffer. That's what it says here, which is different than what it said over there. But fuck it. I mean, the name makes sense. It's just the description here is a little silly. Maybe this is like extra information, right? Maybe this is saying like this is an interrupt buffer, but also if you're in device mode, you will see buff status. Okay. So let's add that to our registers field. So this is on SIE control. We have this guy at bit 29. Okay, sure. Blaze it. And then I guess when we set this guy, let's say that we're going to initialize this like fully at this point. Maybe we'll find that we need to modify this in multiple stages, but for now, let's just do it all at once. What does he want? Missing struct. Oh, it's int 1 buff. Interrupt every 1 buffer. Okay. So we restart this thing. And we start our packet capture. Run. And we see that this guy's starting to spam shit, but we're interestingly not seeing anything at endpoint 0. So I think probably we have to define something somewhere. I don't know where, but like clearly we're like, well, I guess it's possible that our interrupts aren't configured correctly. That's like a definite option. But my guess here is more that this isn't happening. I guess we can also check the buff status field in this while true, right? We can just look at that buff status register, right? Where the fuck that is. And we can just see if we're seeing any evidence of this thing getting modified, right? So if we're getting stuff in, we should be seeing EP0 in get set. So, ooh, write to clear. This is a write clear register. I don't know if this means that we can read it. Where does it explain to us like what these things mean? Somewhere in here it tells us like write clear, write to clear, WC. Here. Clear types. Read returns register value. Okay, so we're allowed to read this guy. So we should be able to be like buff status and buff status. This is here. Actually, for now, I don't really feel like defining a type. Let's just read it. So we'll just, in our while loop, be like, stood debug log debug buff status is a read of USB buff status, right? So if we're seeing something, get written, then we'll see it get written. We should see something in there, right? I'm curious about why you're writing that registers JSON by hand instead of parsing the SVD. Because I didn't have, I think that SVD was XML and I didn't at the time want to pull in an XML parser. If I remember correctly. Is this just like in the SDK or something? Yeah, it's XML. Yeah, I think that's really the extent of it. And I just haven't gone back and fixed it. So it's just like, I also find like, I'm also okay with doing register by register because I need to read the ones that I'm looking at anyways. So it's like, it's fine, right? Like I want to like, I don't know if I want the world as much as I want like the things I want, the things that I want. And to get the things that I want, I need to look at the things that I need to look at them, right? So I'm kind of okay with going through the process. It's kind of like a way to force myself to read. But I think you're probably right. The SVD thing is probably better. Okay. So this lines up, right? Buff status 0. That's lining up with the fact that we're not seeing anything. So it's likely that we need to respond with something more sane. Can we hit start again? Make sure that when I hit run here, we start to see some evidence of some shit happening. And maybe we just look a little bit more closely at, what he's trying to do. Right, so here we get some USB interrupts from the USB hub, right, which makes sense. He's saying like, yo, someone got plugged in. And then here we're talking to the USB hub to ask for status of something. Looks like we're asking for like port power, and he's like resetting this guy. Why is adder 143? Did I not hit enter here? I probably didn't. Okay. So then get status. He's trying to talk to device 0, so that's us. He's calling get status. And we respond with I guess the hub responds with this. Okay, so maybe this is talking to the hub, not to us. Then eventually he like resets a few times. Then eventually he's actually asking for get descriptor. Ah, sorry. 100 is probably it trying to talk to us, and 110 is probably it trying to talk to the hub. That's my guess. So then this responds with protocol error on get descriptor. So I guess I would assume here that we need to populate the memory that the USB controller on our device is responding to this request with. Because my recollection here is that there's just like some RAM that is shared between us and the USB controller, and he just like copy paste that shit directly onto the wire. Right? So if he's saying like protocol error, it probably means that we're not responding the right thing. That would be my guess. So can we look at what this like low level example does? So they have like endpoint 0 description here. And when they call like setup endpoints, they define this register and they set him with the USB DRAM buffer offset. Take the buffer pointer located in the USB RAM and return it as the offset of the RAM. Okay. Sure. I don't really understand what this XOR is doing. But we'll come back to that. Oh, I see. He's either going from offset to, if the thing has the USB DPRAM address in it, then it turns it off. Otherwise, it turns it back on. Sure. So when we go here, he's saying like, hey, I'm going to put this stuff in USB DPRAM endpoint 0 buffer A. And then I am setting up that endpoint control register. Okay. So, and then if it has a descriptor and a handler, does endpoint 0 have descriptor and handler? It does. But endpoint control is 0. Okay. Oh, so they don't actually set up endpoint 0 directly here. Endpoint 0 is set up somewhere else. The fuck? That's interesting. I guess maybe, like they said in the docs, endpoint 0 is guaranteed to be on, so there's nothing to configure here. So this USB setup endpoints is actually not doing anything for endpoint 0. But maybe after this thing is set up, wait until configured. Where does this come from? Oopsies. That's kind of interesting. USB bus reset happens on bus reset. Wait. This is interesting. This is definitely interesting. So this means that we're supposed to handle a reset, which is like one of the first fucking things that happens, right? They're sending us port resets right now, and we're just not doing anything. So they're in the USB interrupt handler. We're not getting into our USB interrupt handler, but does that mean that we've like accidentally masked it? We have some interrupts, you know, IRQ. Is it this? Fuck. Where is the like interrupt? Here. Okay, so one of these guys is like a USB interrupt, probably 5. Offset by 16 though, if I remember correctly. So this is 21 is the interrupt that should be firing. I believe. So when we go in here, This is like the last thing we do, so we should have the interrupts in an interrupt table here. Okay, so it's not like we're like intentionally skipping 21 or anything. Interesting. So that means that we're not getting that interrupt handled. And I assume that they're in the SDK, this like ISR USB control, I think this is just some like bullshit that they hook up directly to that interrupt vector table. I think like when the processor goes like, uh-oh, shit happened, they just call that function, but we should double check. ISR USB control. Ooh, maybe I was wrong? Oh, ISR RQ5, I see. And then ISR RQ5. Yeah, they just throw this into the interrupt table. So this is in RP2 common, Pico CRT0. And so, yeah, they just slap this shit in there. I'm pretty sure. So if it's declared, they put it in the table. Yeah, that looks familiar. So it should... We have a thing configured, which to me makes it seem like we're not getting that enabled. Oh, because enable USB interrupted processor. This is what we're missing. IRQ set enabled. So... I don't remember having to do this for like GPIOs and stuff, but let's take a look. So this is going to be in the SDK, I guess, huh? IRQ set enabled. Probably is like a void function. So this writes to the this does look familiar. So I guess this is like a maskable interrupt, I guess, and some aren't. Okay, and Vic. Let's take a look at this guy. Okay, external interrupts can connect to this guy. He prioritizes interrupts. Blah blah blah. He's writing to Iker and Isser. So clear pending register and set enable. This is the interesting one. So I'm confused about like why this isn't a problem. Oh, maybe the interrupt is like, I wonder if I like fully unplug and replug this thing, if we'll start seeing that interrupt fire or something. Like if it's like, if we have to clear it from somewhere else. Use the interrupt set enable register to enable interrupts and determine which interrupts are currently enabled. If a pending interrupt is enabled, NVEC activates the interrupt based on its priority. If an interrupt is not enabled, asserting its interrupt signal changes the interrupt state to pending. Okay. So this is this one. Use the interrupt clear enable registers to disable interrupts and determine which interrupts are currently enabled. So if enabled, I see PR. Forces interrupts into the pending state and shows which interrupts are pending. So here, he changes it to pending automatically. Why would I want that? So ICER is clear enable. That makes sense. So if it's off, he turns it off. I don't understand why you would set pending on an interrupt when you turn it on, though. Oh, he's clearing pending. He clears pending. I see. So he's turning it on and making sure that, like, we don't accidentally trigger an interrupt from, like, last run or something. Sure. That seems reasonable. Understood. Okay. So we just need to talk to, you know, this guy. Oh, and we have actually done this before. I see. We did this intentionally for the GPIO one before. So here we probably want to I see. So let's enable in init USB. Before we will probably like turn the USB controller off. Clear pending requests at hold on. Probably 5. Because we were using 13 for GPIO, so this is 5. Okay. So now this interrupt should be enabled for this guy. But we don't see any evidence of that happening. Okay. What if we did just like something stupid? And just fucking let it go crazy. Interrupt everything. So we're hitting 22. Oh, which is probably this guy. 16 plus 6, 22, yeah. Okay, so turn off that one. Unplug, replug, maybe? Maybe it's like stuck on from before. No. Interesting. Oh. Oh, I'm a dumbass. I'm turning everything. I'm trying to turn this one off. So probably XOR is actually what I want to turn it back off. My bad. Okay, now we're hitting 31 a bunch, which is up here somewhere. So I guess this means that like the masking is kind of working we expect. What's 31 minus 16? So this is this single IO RQ proxy. Okay, sure. So I don't know. Let's just turn stuff off until we start seeing interrupts that we don't want. You should probably read first and only turn on the bit you want before writing, huh? Yeah, probably. I agree. I agree. But for now, I'm just trying to like get like, I'm just trying to understand what I'm looking at all. I'm just trying to see like, can we get it to trigger a USB interrupt? I don't really care about like nuking everything else for now, which is not happening, right? So that means that like somehow their example is getting the USB one triggered and we're not. Right, and we see evidence of like obviously messing with this register is changing other stuff. Right, so it's obviously having like an effect that makes sense. I'll put a fix me here. Obviously read, modify, write, so everyone else doesn't get effed. Do we have a interrupt handler set up? We should. So what I did was on the interrupt controller or init interrupt table, I have like a do nothing at blank for every single item, and in there I just breakpoint. Right, so we should be hitting like do nothing 21. Right, we should be hitting this. Does it get overridden by the GPIO one? I did just check that, and I don't think so. Because the GPIO one happens first, and then also we're seeing interrupts for all of the ones that I just tried, so. Right, the GPIO one's getting done here. Right? And then we're doing all the stuff we care about here. So, like, I think it's fine. I think. And then also, like, this is the last thing that runs before we loop forever. So, like, literally nothing else should be fucking with us here. But we could just go back to their low-level example and see if we missed something. Seems likely. Okay. So we did this. I'm pretty sure we did this. We didn't do this. Maybe that's relevant. We did not do that. And that does seem relevant. They're like, let's set some, like, enable interrupts on the inti. True. True. We do want interrupts if we want interrupts. Inti. Oh, yeah. Hell yeah. Hell yeah, dude. USB inti. Okay. So I guess we'll just start with the ones that they do. Setup. I guess we can actually just do... Let's do this. We'll do our classic... And I think that this is actually not just inti. I think this is int f and int s as well. So we should really just call this like USB int or something. Hello, I'd like to copy paste this, please. There we go. USB int, we'll call this. Okay. Delete anything that doesn't start with a number. Like this. And then we do some like vim macro bullshit. Record a macro, find the colon, you know, delete everything, go back, delete this word, paste it, colon, delete this space, and then put quotes and lowercase it. Cool. Zig build. All right. That is okay. And then we go over here and we have inti. And then this is int initialized at base plus the inti field. Well, so here we're gonna copy what they did. So we set all fields that we know about, and they set I guess if we're setting everything, we need this. No, this. Bop. Oops. Okay. Put a dot, find this, equals 0. And then which ones did they set? They set bus reset, which is probably the one that we're looking for, right? And then also buff status, which we know is not the one we're hitting. And then also setup request. So I'm going to say only do bus reset for now, because I think that that's what we should be seeing. No bueno, huh? Interesting. I mean, I guess we didn't do this, but that seems unlikely to be the problem to me, but I guess we could try it. But everything else we've done, right? We enable... Did we do it in the same order? So we take the guy out of reset. I guess here, technically this shouldn't matter. Shouldn't you be getting a set request? I think that we're getting reset first. But yeah, I guess maybe you're right. Maybe we should double check. You know, maybe setup and buff status, fuck it. We might as well try it. I don't think that we should be, but yeah, we're not getting interest for those either. I think that we're, like, my understanding is that we should be getting a reset first, right? That's kind of, Actually, maybe not. Maybe you're right. Maybe it is a setup request. Why isn't this running anymore? Oh, that's interesting. This is interesting that this is no longer doing anything. That's quite concerning. Did I accidentally delete the part that turns us on? I think I might have. I guess we also do this. We are changing the interrupt status after we turn on the pull-up, which seems bad. But again, like, I feel like we should be seeing something happen here, which we're not anymore. Right, I'm not high, right? We used to see, you know, bus information, like, stuff happen. Okay, here we go. Okay. I think we're seeing it again now. Reset. Run. Boom. Okay, good. We're back. I don't know what the fuck was going on there. Okay. So yeah, I mean, it could be this like get descriptor response being protocol error. That does seem kind of that is where we were before. It just seems strange to me. Yeah. Okay. So here we have setup requests, bus reset, buff status, all as things that we want interrupts for. Okay, let's just like look for differences between what they did and what we did. Okay. Clear any previous state of DP RAM just in case. We didn't do that, but I'm kind of okay with that for now. I guess we could see if this guy is just responding. Like, if the response here is, like, flagged by what we have in DP RAM, that'd be interesting. That's something to look at. Then we do muxing modify to match what they did. Great. We don't touch power, right? So, like, fix me. Do we need to force VBus detect? That might be relevant. Then we enable device mode here, which is great. Then we enable I see. So they did this here. They did this in 2 steps, right? They did set the enable interrupts here, then set the things we care about, then turn it on. Right, so they did like pull up enable 1 here. I don't think that should matter, right? But maybe it does. If like the modifying of the interrupt enable flags only works if it shouldn't. That should not matter. Yeah. Does not matter. I'd be interested to kind of maybe turn all of these to 1 and see if like maybe we're, you know, doing something brain dead. You know? Let's just kind of see. And then we actually might want to clear pending interrupts on the controller, although I guess that should be handled by the fact that we reset it. Okay. I want to make sure that if I reset this thing now, let's start some capturing. Let's just make sure that he is still trying to talk to us when we turn it on. Boom. Yep, he is trying to talk to us, and we are seeing nothing. Okay. So, I mean, it does seem like we're kind of at a loss here. Trying this VBus detect thing seems reasonable. Actually, I'd rather look at the DPRAM thing first. So I'd be interested to know if we see any evidence in like these get descriptor responses. If we just like slap some ones in there or something, I'd be interested to see what happens. So there's like some stuff about like endpoint 0 shit. Let's look at like, I think it's everything is it said endpoint 0 is offset, some offset from DPRAM. Like USB DPRAM at its base followed by registers. So this is where DPRAM starts. Whoa. USB control base. Am I fucking mental? What do they have this defined as? Oopsies. 501. Ah, we have registers here. I see. I see. Okay. DP USB DPRAM is gonna be like a slice, I guess, of U8s. Stud mem. What is it? Slice. There's a way to like convert a pointer and a length. Slice. It's something to do with this like len field, this len thing, I think. Takes a sentinel terminated pointer and iterates over the memory. Right. So here they just say span. This is what I'm looking for. Takes a sentinel terminated pointer and he just returns pointer slice this way. Right. So here we say I think it's like this. So we say const DPRAM pointer is, you know, just some pointer to U8s from this. Except it's not 1, 1, it's 1, 0. Okay? Then we break block with DRAM pointer from 0 to however many bytes this thing is. Right? USB DPRAM. Which I assume is just as until it hits the registers. Probably, right? It's gotta be. And then let's just make sure that this is right. Okay. So can we just do like a memset DPRAM 1? Or even like this? Okay, so now the question is here, when we saw like get status and shit, I wonder if we see any evidence of this being different, right? So before, we had like get status was returning something that looked like this, right? Like stuff, then like a bunch of fucking zeros. So now when we're down here and we respond to get status, this looks essentially the same. But maybe get status was the wrong one. Maybe it's get descriptor is what we're looking for. Because that thing is actually trying to talk to the device. right? He's got device after, so kind of before we're seeing device, we're responding with something that looks like this. Can I like copy this or something? So zeros from 20 to 30 or something like that. Okay. That's like identical. So it doesn't look like doesn't look like we're seeing any evidence of that RAM being like shown in the responses here. I don't think. I don't think. Okay. And then I assume that setting 0 here doesn't really change anything either. I assume. Yeah, nothing really too interesting going on there. Okay. So then the next thing to look at is that like the fact that they were forcing that VBus thing. That really just doesn't sound right to me, but like I guess fuck it, it's like our only lead right now. So they did that after muxing. They did USB power modify, and they did VBus detect 1 and VBus detect override enable or something, right? Something like this. Is this still running? We gotta make sure that we're not like just killing our RAM. Blah blah blah. So we're looking for something that's like power, USB power here. Fuck. Something like this. Okay. Registers. We got USB power. Fields. And what we got here. Overcurrent detect. VBus detect. Sure. Delete word and paste like this. Quote, quote, lowercase, go, 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 go. Okay. Cool. Cool, 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 cool. And then this is registers USB power init base plus whatever the fuck this is. 78. Hi. Hi. What's he pissed about here? Const power. Expected expression found const. What the fuck? LSP restart maybe again? Yeah, okay, there we go. I don't know what the fuck is complaining about, but comp time combine maybe. Leave everything else the way it was. I don't really give a fuck. Then this is like, is that right? Yeah. I don't think that this should change jack shit, to be honest, but if it does, I'll be a little surprised. All right. I was wrong. I'll allow it. I'll take it. So I guess that means that, like, he's, like, struggling to understand that this thing is connected? Like, what the fuck? Overrides for the power signals in the event that the VBus signals are not hooked up to GPIO. Set the value of the override and return the override to enable the switch. Interesting. I don't understand this. This doesn't make sense to me. Okay. But I guess we'll just write here. Unsure why this is needed. However, interrupts were not firing before we did this. This is a copy paste from the dev low level example in the Pico examples repo. Don't understand. Don't understand. Okay, so now we can go back here and go back to turning everything off on which interrupts we respond to. And we should be able to say we are expecting that we're expecting to fire an interrupt on buff reset, right? That's what we're expecting right now. Boom. Okay, that's huge. And then let's just double check as well if I turn this back off. Sick. Boom, 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 boom. Let's go, fucking baby. Let's go. Okay, so I guess that means that we've like prove we get data is maybe like notice any bus activity, I guess is kind of more what we've done here, right? And now we're kind of like, okay, let's handle the bus reset. Handle bus reset, right? So I don't really know what that's supposed to do. What do they do in the low level example? They kind of move into configured state here, right? Oh, configured false, actually. Sure. So they just like go back to default state, I guess. Oh, sure. So if somebody unplugs and replugs us, we need to like uninitialize everything. So, and then do they answer anything here? I don't know. And then how do they know that this is a reset? Right? That's the next question here. Is they look at the interrupt status and they check if it is reset. I see. Sure. Sure. So we add an interrupt status flag here. Wherever the fuck we are. And where is that like status? USB int s. Oh, maybe he doesn't get like a nice name like that. Maybe it's just int s. Yeah, it is. So it's 98 for status. Okay, so we want to override our like interrupt table with the idea that interrupt vector table at 21 is going to be USB RQ or something, right? I don't know why the syntax handling is so fucked. Let's restart. So what do we call it? We call it like USB IRQ. So first, let's just make sure that this function gets called instead, right? So we should see breakpoint in USB IRQ. That's so big for us right now. And then here we look at the... Okay, first of all, also, let's... make sure that this guy is back correctly. I guess we probably want to unplug replug to make sure that that's getting hit in the fully cleared state. Okay, cool. Everyone's happy. Okay. So here we look at USB int s. Read. Status. And we say if status dot bus reset breakpoint bus reset as a function is equal to 1. So now we should we are hitting the breakpoint on that, and then we probably have to clear that flag as well, right? Almost certainly. Are they? Yeah, they're setting it handled. I see. So here we go, like status. Uh, do we write to the same status flag? Read only, right? So it's not here. It's probably on interrupt. Where are they running into? Do they not? Are they not clearing the interrupt somewhere? Hardware clear. Bus resets bits here on SIE status, probably. Is that what's happening here? That SIE status is right to clear. Yes. Okay. So here we go. USB SIE status. This guy has bus reset at 19, right? Yeah. So, ugh. I don't know how well our thing handles this. Yeah, we don't really handle, like, we only really handle read, modify, write stuff in our register abstraction. Which this is not great for. Fuck. So, like, typically we intentionally do, like, read. We only allow ourselves to get registers by doing a read, modify, write, with the intent of, like, making sure that anything that isn't, like, a reserved field, we kind of leave the way it is, because we didn't really understand, we don't really know what those are supposed to be, right? Like, if we see something in these reserved fields, we shouldn't touch it, is kind of like the default assumption. Now here, we actually only want to write ones to the bits that matter. So maybe here, if we know that it's a write clear thing, we could maybe flag things as write clear, which allows us to write to those things without anything else. Or we just like bypass the register abstraction in a way where like maybe our thing that's generated has the bit offset for each of these guys, and we're just like allowed to bypass in that scenario. I think that's reasonable. Let's do that. So generate register types. I think what we'll do is just kind of, we'll make like a section that's like offsets, and we'll iterate all of the elements that all of the guys, and we'll just write them down somewhere and we'll just bypass. I think that's fine. So I guess we probably want like something that's like write offsets. And in here, what's happening? So before we were like iterating over fields. What are we using this allocator for? Oh, to generate the type name. Sure. Which we don't need here. I think it's more like we're writing like self writer write all, and we're making like a struct offsets, const offsets is a struct, right? Then we're writing for each field, we're writing something that's like const name of the field is equal to some number with a semicolon, who's going to be like field.value pointer, I think. And I guess we'll only do this if the value pointer is if start equals end. Or maybe we can do the range. Maybe this is always a range. So this is like two comp time ints that are this and this. Yeah, that seems like reasonable. So here we go, register field start and end. And then at the end of all this, we have to close the structure. Are you proficient more in Zig or Rust, and do you find Zig more enjoyable? I don't know. I think that doesn't really matter. Is kind of like my overall opinion. I think that I prefer Rust for now, because it's more flexible. Is kind of my current stance. I guess the reason that this didn't change is because I have to do write offsets, or else he's gonna be mad. And then here, we're not using this fixed buffer allocator at all, I don't think. Okay. He does want the fields, huh? Definition. So what's he mad about? Found array hash map, expected type array hash map. String hash map unmanaged. I guess we'll just do whatever we copied from, which is just not dot map. Got it. Maybe we could have done that. Area union is ignored at 244. Try here and here. All right. Okay, and that seemed to work. Let's see if we jump here now. Do we have offsets here? We do. So now on, which was the thing we were trying to look at? The like int status here. We should have registers. We should have offsets somewhere for all of these guys. And all of these guys are single bit. Nice. Okay, that works. I wonder if masks here makes more sense, actually. Yeah, I think masks makes more sense. Which we actually kind of already have. I kind of just changed my mind. I think we don't need that offsets thing at all. I'm going to comment this out for a second. And it should actually just be that we... I forgot that we had this. So we should be able to be like... registers dot USB int write mask. Oh yeah, this is actually exactly what I wanted. So this should be like USB SIE control reg is equal to this. Yeah. And this returns a write mask, which is weird. But we can do like this. Yeah, that's not the end of the world. And so now this should happen... like once per thing that happens in Wireshark. Continue? Continue. Not looking too promising, huh? What if we just like full? Oh, is SIE control the wrong one? Did I just do a fucking dum dum? Is it SIE status? I think I did a dum dum. It should be SIE status. My bad. My bad. Um. My bad. Sure. We'll make that work. Okay. So if I clear everything here, just for shits and giggles. There we go. Much better. Okay. And then let's do another runny. So we hit this breakpoint once, twice, 3 times. So this is, I guess what we should be doing here is we should be looking over the rest of the fields and seeing what's getting hit. That's kind of more interesting, right? So can we iterate these things? Kind of. Because this guy returns a value. I guess we'll just do this. Stood log info. Maybe we just breakpoint here and look at the status field. I think that's probably the easiest thing to do here. Okay, so this is 1-bit set at 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So bit 12 is set here, which is what? Oh, this is bus reset. It is only bus reset. So how come clearing this thing is not doing anything? That's interesting. Right, am I crazy? P status. P status. P status. Yeah, weird. Because I would think this should be happening, right? By clearing this, right? If we did the stupid thing here and slap this with Fs, it seems to be clearing it, right? Yes, that only triggers once. So why is that different? Can we look at the SIE status register? Oh, maybe it's like some of this stuff is happening that is not one of these interrupt. Right, so maybe these errors are not the same as the other stuff. In fact, does this register even map the way I think it does? Like, we got bus reset at 12, which is 19. Yeah, this is just a different fucking register. I'm just a dumbass, is the answer here. So SIE status should have his own type. That's the problem here. My bad. My bad. And so it was actually bit 12 of status, which is reserved. Oh, because status and control. My bad. I'm just a dumbass. I'm just a dumbass. I went to highway. Sure. Okay. So I guess we'll just do, for now, bus reset 19. And we'll come back for the rest later. Okay. That should be way more reasonable. So we hit this once, never again. Let's go! Okay, cool. So handle bus reset. Technically, we don't have to do anything, so I think we call that, a day. And presumably now, he is going to be sending us some setup requests that we actually have to like answer properly, right? So presumably we turn on setup request here as a thing that we care about. We hit this once, then this should now be the setup request, right? So if we look at status now, that's still reset. Oh, but now this is something else. This is 4 more bits up. So that's bit 16, which should be bit 16 is setup, right? So now we're getting a setup request. Hype. And if we look at what it's sending, it's probably like, it's got to be that get descriptor, right? So let's look at what their low level thing does. When they get setup request bits, they call handle setup packets. They clear the setup thing. And here they look for what are they looking for? So they have the setup packet area in USB DP RAM. Nice. Which are just the first 8 bytes. Then they process this thing as like a USB packet. Okay, so let's see if we can do that. Okay, so we should, from our other experiments, have some of these structs that we want defined already. USB user space test source main. In here we have like, the USB descriptor thing. I don't know if that's what they are expecting to get in the first 8 bytes. What was it? It was handle setup packet. So they've converted this to a setup packet, which is this. So do we have that defined somewhere? No. Not that I can see here. BM request type. Okay, request type. Yeah, okay, so that's not defined here, so I guess we define that ourselves, and I guess we just copy this. Right. So we go, oops. Maybe we go packed struct like this. And sure, we can use the same request type, request value, index, and length. Let's take a look at this. Okay. So here we should be like, if status setup, what was it called? It's called setup rec. If we are a setup request, first we clear, the setup mask, which needs to be on that SIE control shit. Oh, that's SIE control, my bad. This one. So SIE status should have setup request is 17, so setup rec, what was it, 17, I think? Do you have some suggestions for getting low-level programming? I have no experience with low-level work. I'm back an engineer. Yeah, I think just like do something, like I think that these like microcontrollers are actually quite accessible. Like this like Raspberry Pi Pico that we're working with is like pretty straightforward, but you got to find like an excuse to do something with it. Driver work again, it also is like not too crazy. But I think that like for me, it's always like find a thing that I'm motivated by and then just do it, and then like eventually you'll just have to get through the pain. It was setup rec in the docs. What did I call it? Oh, I put a Q instead of a C. Find thyself a problem, and I got lots of problems. I'll tell you. I don't like that it's rec with a C here, but Q in the other one. But I guess like fuck it. I guess that's the way it is in the doc, so we should match that. Okay. So we have to like let's start by just like processing this thing in some way. So let's say that we have like USB set up, and we want to look at DSP DPRAM. So we want to do like std mem bytes as bytes 2 value. I think that's better. I think it's bytes 2 value. And we're going to turn this into a USB setup from USB DPRAM. Okay. And we should just be able to like look at this setup thing now. So that's the reset. Okay. That's great. Love to see that. That's cool, man. I would have loved to see like, you know, the fields of the structure or something, but I guess if you just want to throw me a big ass fucking number, that's cool too. uh God damn it. Can we do this? Just kind of like log the structure. Will it be a little bit smarter if we do it this way? Fuck. We might not be able to log like that from within a interrupt channel like that. Not really sure. Yeah, that sucks. Yeah, I mean, I wouldn't really expect this to work, to be honest. God damn it! I just want to look at the fields, man. I guess we can do this. This is fucking stupid, but this should coerce the debugger into showing me what I want. Const this is equal to paste setup dot delete. Okay. And then I guess for all of these, we want to go like this equals thing like this, and then breakpoint, which is annoying, but we'll live. All right. Boom. Info locals. Boom. There we go, baby. So we got request type 0, request 5, value 18, length 0, index 0, status 6335536, where status is something else. But okay, so if we go and look at, I guess in Wireshark, what this thing was sending, I wonder if that's helpful. So this is going to be like somebody was talking to device, probably this guy, right? So we have request get descriptor 6. Maybe we need to look up what these things are in the USB spec. Maybe that's the play. Where the fuck is the USB spec here? So this is a setup request, so we're probably looking at the protocol layer. We're looking for like definitions of setup. Can I just look up like get descriptor? I know that that's one of them. Wait, is this the right thing? Refer to table 9.3. So we're getting 5. Oh, which is set address. Which is set address. Hype. And then this is just device request. Okay, so he's saying like set address. Sure. And he's saying set address to 18? Ah, wait, that seems hype. Okay, so what do they do in their example when they call set address? So this is actually answer set address, but we don't know. We didn't know that when we started. Set address, right? So he says like we call set address, which is just citing dev adder. Is this used anywhere? Oh, here. He says set it in hardware. Confusing. Handle set adder request. The actual setting of the device addresses hardware is done in EP0 in handler is because we have to acknowledge the request first as a device with address 0. Got it. I see. So then how does EP0 in handler get like hooked up? It's got to be from here. But when he calls, when he iterates these endpoints and sets them up, wasn't it that like wasn't it that he skipped anything that was if he doesn't have endpoint control? Oh, okay. So do we have endpoint control on endpoint 1? He doesn't, right? So how does this callback ever get set? Must be through this handler somehow. Ah, USB handle EP buff done. Handle buff done. Handle buff status. Which is done in the interrupt handler. So he handles the setup packet, then he just calls set device address, which doesn't do anything, right? Oh, he acknowledges the request. He acknowledges the request, and then he sets the address after. Yes. Okay, which is fine. So what we should do, he's got a lot of stuff going on there. A lot of indirection. We can get away with just being like, we need to figure out what he's doing when he acknowledges the request. So he starts transfer with like this endpoint configuration. God, there's so much indirection here. But like, what's he actually doing? Start transfer of length on endpoint address this. So he prepares buffer control. So he says he has some like global length field for probably some like circular buffer shit that he's looking at. Oh no, this is here. So he's saying, yo, we've got buffer null, len 0. Okay. Copy the data from the user buffer to the USB memory. So if this is an output endpoint, is tx. If USB dir in. So I guess in, I think everything's from the context of the host. We're the device. So I think in is a transfer to the device, to the host, I think. So we're probably here. And then he marks the buffer as full. And then he sets the double buffering shit. Oof. Right, so there's some buffers in like shared memory. I think we check if they're available to see if the USB controller is done with them, and we set them as full if we want the USB controller to do something. And then here, they must be saying like, they must be saying like, hey, we have 2 buffers, pick the right one, I think. But I don't really know where this like next PID is used. I mean, they're also just resetting it here, so there's all sorts of just like fucked up shit going on here. So there must be some address that we write to that we use to configure which data buffer is used to respond to endpoint 0. Right? So when they is there just like one data buffer that is always the guy we use? Let's try to find this. So here, I think that they have this kind of set up here. USB DPRAM, endpoint 0, buff A. Assume single buffer mode for endpoint 0. I mean, that's... Oh, okay, sure. So A and B are just both the same. No, these are sequential pieces of memory in DSP or dual port USB RAM. Understood. Okay. My poor little brain, I'm struggling. So then they just write, this can be carved up as needed, right? So this stuff is fixed. Endpoint 0 buffers are fixed. We just have to put those in there. And then surely we need to write to somewhere here, buffer control, right? Surely we have to say, aha, yes. So we say there is this much data to send back, I think. So they populate the data, they copy the data that we want to send back into, they copy data into dual port RAM. Then they mark it as full, and I don't remember what available is doing here. So they're marking it as full and available. Okay. Yes. Then they just write that value here. And here they would also write like which buffer to read from. I think I understand. So there's a control buffer that has how long am I? Am I available? Am I full? Who do I read from? Then we set all of those things and populate the data of where he's reading from. That makes sense. Okay, so we just obviously want to find this like buff control register. Right? So... Here. Okay. Okay. So here are all of the control. Haha, I see. So we have in dual port RAM, we have the setup packet, the first 8 bytes, then all of this shit, which is in control. This is interrupt control, and then also buffer control. Okay? So they're probably running to this guy. Then here is where the buffer is. Understood. And then this guy's 40 bytes. Okay. So we need, in our data sheet, somewhere we want to say, probably like USB DP RAM. We probably actually want to define this as a structure. Whose like setup here is going to be a slice of U8. Base, we want to set to like this. Then setup, we're gonna do like this shit, where we say, we basically cast this to US, maybe set up the definition. It's fine, it can go there. USB setup. Which means that this is actually a pointer. This is probably like a USB setup volatile pointer. Yes. Which is pointer from int base. Okay, wait. Okay, we're getting somewhere. Then we have EP0 control is going to be a volatile pointer to control. Now, I think that in this DP-RAM, we're allowed to write things like however we want. We have like byte addressable memory where we didn't in most registers. I seem to remember reading that somewhere. So we should have EP0 buff control. I think that's what we're trying to write to. And this is going to be a buff control, which is base plus 80. Cool. And then we should also have this guy, which is a pointer to 40 bytes. Hex 40, actually, I think. I think that this is what we saw. That seems kind of reasonable. Then we just have to define the buff control. Which is just a packed struct. This is not going to use like our register abstraction because the register abstraction is built specifically for 32-bit writes everywhere, which is not the case in this scenario. So we want to do EP0 has no control register. Oh, that's control, not buffer control. Buffer control's here. I can't remember if Zig packed structs go high bit to low bit or low bit to high bit. Zig language reference. Packed. All packed structs have a backing integer, which is implicitly determined. Each field of a packed struct is interpreted as a logical sequence of bits. Arrange from least to most significant. Okay, cool. So this we should say we expect this thing to be U32. And we're starting at the least significant bit. So this is buffer control. So we're starting here. This is a 10-bit transfer length. Which, do they have like fancy names? No. So we can pick transfer len 10 bits. Then we should have 1 bit of available. Available 0 is U1. Stall. Reset buffer select to buffer 0. Clear to end of transfer. I don't know. Fuck it. Data PID. So we're always going to use 0. Last buffer of transfer for buffer 0. Last buffer of transfer. Okay. Buffer 0 full. Full 0. And then this is also 10 bits. Transfer len 0, I guess. Transfer len 1. Then this is double buffer offset. So this is 2 bits. This is PID 0, I guess. And I think it's last transfer 0 as well, right? Yeah. So this is PID 1 and last transfer 1. Then full 1. And this should be 32 bits. You skipped available 1. Yeah, I did. Okay, so this is 10, 11, 12, 13, 14, 15, 16, 26, 27, 29, 30, 31, 32. Yep. Okay. Cool. Cool. So this should be the right size. And so if we're handling this thing, it should be that we write into the EP0 response buffer, which is, what are they writing, by the way? They're writing 0, right? So we actually don't have to write into that buffer at all. Their ACK is, because we saw here, null 0, right? So they're like, fuck off. But maybe we mark this as full. It depends on, like, EPTX checks if it's in, which, how do we know that? That's from endpoint here. So they're using EP0 in address, right? So this should be in, right? Should be. Then, actually, that's not clear to me. But at the very least, we should be marking as available. We should be marking data 0 PID. USB DPRAM. I guess we never. The fuck? USB D. Did I spell it wrong? USB DP RAM. Oh, USB. I'm a dumbass. USB DP RAM dot EP buff control. And then we have to write out all of these things that they wrote out. So it's available 0. Right? I assume that's what they're doing. This is bit 1, 2, 3, 4, 5, 6, 7, 8, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So they're setting bit 10, buffer 0 available. Okay, yep. So that lines up. Full 0 also. Oh, but they're actually writing this, they're not writing this out yet. Right? So they're actually kind of doing more. USB DPRAM buff control. They're kind of saying, like, they do it all at once. You know, out is this. Control val. I guess here we initialize everything as 0. So we can default initialize this guy. And then they go like control val dot transfer len 0. This is 0, which is great for us. You know, full 0 is 1. They set available 0 to 1 as well. They set the PID. So we're going to use data 0 PID. Which is, oh, I see. It's like which one are they using? So this is at 1, 2, 3, 4. This is at 12, 13. Data PID. I see. Am I fucking stupid? 10, 11, 12, 10, 10, 11, 12, 13. Okay. So how can we have data PID 0 and for buffer 1? This is just 0 unconditionally, right? I think so. Oh, I guess maybe we have to flip-flop? I'm not sure. Because we saw something about them always using PID 0. And then, so I guess it's just this is 0. Confusing. Not sure about that. Something about that feels kind of fucking weird. Then they just write this shit out? So they go like, this is equal to control val? Okay. Sure. So then after we respond with this thing, then are we chill to just like set our address now? Or did they have to... Right, so they're like in their reset handler. They handle setup packet, which means that in here they acknowledge the out request, which means they start a transfer. And then after that, they come down here and wait, where was it? Where did they actually call set address? EP0 in handler, right, which was called by the IRQ handler. He looked for buffer status, maybe? Iterated over? No. Somewhere, where does he call the handlers? USB handle EP buff done, which is in handle buff done, which is in handle buff status. Oh, I see. So you start the transfer, then we have to wait for endpoint 0 to be finished writing. So what we're hoping to see right now is we're hoping to see buff status come through for us eventually. Right? So we kind of like run this shit. Oh wait, don't we need to write the value somewhere? So yeah, it's like this is address set later, right? We have to wait so that response happens on endpoint 0 still smile. Right? That's kind of where this goes. So we're hoping that like we run all this shit and then eventually somebody goes, hey, bro, endpoint 0, he's fucking donezo. So if we go back to logging this buff status thing all the time, eventually this should start saying something, I think. And then we should turn on this interrupt. Yes. Okay, so bad news? Nothing's happening? Did we not clear the setup request interrupt? Or maybe I'm just confused because... Oh, we do clear this thing. Maybe something is happening, we're just not, hold on. Okay, so some stuff did happen. And it looks like we sent get descriptor and just nothing fucking answered. This is different than the behavior we were seeing before, huh? So like we aren't seeing the set address thing happen in Wireshark here, which just kind of makes this whole thing kind of hard to debug, right? But also here, we're probably seeing another setup request that isn't this one. We're probably just always doing... We're probably just always answering like it's set address, which is wrong, right? So we need to like switch on request. That makes more sense. So here, it's like if this is anything that we haven't done before, we'll breakpoint on. And if it's 5, which is set address, I think, then we do this. Right? That seems kind of reasonable. Okay. Okay, so then we run. Okay, so that's not good. Right, that seems bad, like nothing's really happening. Handle setup request, bus reset, buff status. Okay. Did we ever turn on that, like, set buff status on endpoint 1? That's this one, right? Pretty sure that's what this was supposed to do. And then also we're not seeing buff status change. So that's interesting. It's hard to know if that means that the thing is sending or not. Right? The fact that this was always this, we don't see any like 1.1.20 or anything, right? Is kind of suspect. I want to read the definitions of what full and available mean again, because it could be that we're misunderstanding here. Okay. Is used to indicate who available is used to indicate who has ownership of a buffer. This bit should be set to 1 by the processor to give controller ownership of the buffer. Right, so that's what you're doing. The controller will set the bit back to 0 when it has used the buffer. The available bit should be set separately to the rest of the data in the buffer control register, so that the rest of the data in the buffer control register is accurate when the available is set. Okay, cool. So like don't write available at the end. What about full? Full. Buffer 0 full should be set to 1 by the processor for an in transaction and 0 for an out transaction. Control sets this to 1 for an out transaction because it has filled the buffer. So if we're responding, we set it. Otherwise, the controller is in charge. Controller sets it to 0 for an in transaction because it has emptied the buffer. Okay. Okay. I would be maybe interested in reading what this thing looks like before we start. EP0 now is gonna be USB DPRAM dot EP0 buff control. And then can we breakpoint on this? Okay. Let's take a little peek skis. What we looking at? I guess we have to breakpoint, which we did. Wait, then what's the problem? Hello? Is something wrong? Maybe I'll full unplug replug. See what happens. That's a little confusing. We must be doing something. Oh, is this supposed to be request type? Not request. Hold on. Let's go back to the USB 2 spec. Request. Request type, request. So yeah, it should be request is set address. And request type should be 0, right? And like we should be breakpointing in one of these two paths. No? We either breakpoint here or here. So why the fuck is this not getting hit? Hold on, something's wrong. Okay. So here we're at 847. This is confusing. Because I swear we were getting this setup request before, no? Am I stupid? Breakpoint here? Confusing. And yet Wireshark is still seeing something happen? Oh. Interesting. Very interesting. Because I swear we were getting this before. So what are we getting instead? I assume it's just the status request a bunch of time? Or the reset? Oh, did I breakpoint at the wrong time? Yeah, I did. So this is... I believe this is... reset? What the fuck is going on, dude? Okay. So, reset. There, here we go. This is a setup request now. Weird. Okay. So now we're at 841. Sig trapping? At 841? What the fuck is going on? It's confused. Okay, so now we definitely are... Can we do like a... I don't know, man. I guess we should just leave this the way it was. Okay. Zig build, run. Continue? Weird. Oh, here we go. Okay, wait. P status, reset. P status, setup. Okay, now we're at the breakpoint here. P, we're gonna continue. We are here. Okay, we're right here, we're here. So we should be able to say print request. This is a set address request. Continue. Which we might have taken too long to answer. So the controller might be a little bit upset. So let's take this breakpoint away, and maybe this breakpoint away, and even this breakpoint away, and let's see if we ever hit the other breakpoint now. It seems like it sometimes takes a while to get there. So we wait a little bit. We just see if we ever hit the other breakpoint. We do. So now we are right here, and can we print request 6? So this is get descriptor. Yes. Okay. Oh, and I wonder if it's because we didn't actually set our device address, so he's probably just fucking pissed that it didn't work. Like, here he said, set the fucking address. Then we're not interrupting when this thing finishes, or we're never answering, right? And then eventually he calls get descriptor, and we're like, okay. But the response here is probably not going through, is probably the bug. That would be my guess. So can we like spam poll this available thing and see? Okay, I need to read the available docs again. Available means that the controller owns the buffer. So what I'd be interested in seeing is in this like spam loop here, can we look at like available on DPRAM, EP0, buff control, available 0, right? So theoretically, when the controller is done with this guy, he should be like, okay, all done Z's. So that's a good sign, I guess, that every use of available does go to 0, even though we set it to 1 here. So that kind of indicates that he, like, finished. But then why are we not getting the interrupt on completion? That's the important piece here. So we're probably missing something here. So EP0 handler is getting called through this like buff status thing. Right? And so they on device init must be setting up stuff that says, hey, enable interrupts when the bus is reset. Also, when our endpoint 0 is finished transactions. I feel like we're doing those things, but I guess we just have to check because we're not getting those interrupts, which means that we're doing something fucking stupid. So this is 8 or 8, 16, 24, 25, 26, 27, 28, 29. This is bit 29 is what they should be setting. Which EP0, EP0, which is what we're setting, right? So we are doing that at least. Then they set on inty buff status, which we are doing. And this is bit 4, which is what we are setting. So then the question becomes, what are we missing? Maybe when they set up endpoints? No, because when they set up endpoints, they're skipping endpoint 0 very intentionally. We saw that. Interesting. It could be in their handler they're setting something that I missed. Hello? USB. Where the fuck is their interrupt handler? I thought it had the name IRQ. Oh, maybe it's ISR? Interrupt service routine? Yeah, there we go. Okay. So it really should. I mean, the bus reset's not doing anything crazy, right? Oh. They are intentionally setting the hardware address back to 0, which is interesting. We might not have done that, but we're never setting it at all, so it's like, should be fine. We're also getting. I wonder if he's doing it like internally. Surely not. Okay, then we go into setup packet. He sets the endpoint configuration. Could be that the PID is wrong. He's always setting it to 1. We were using 0, which is probably a mistake on our part. Right? It should be like this. Okay, so that could be it. No, because buff status is never getting set there. So, okay, so that was a mistake, but maybe not the mistake. And then they call set device address, which calls acknowledge at request, which starts a transfer with, you know, the right configuration, and he sets the stuff and he calls it. Yeah. And so this guy is 1, which means that he's saying buff control data 1 PID. Okay. Wait. Oh, yeah, it seems fine. So this is, let's just double check. This is 1, 2, 3, 4, 5, 1, 2, 3, 4, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So this should be bit 13. 10, 11, 12, 9, 10, 11, 12, 13. Yeah. Okay. Could be that we're not supposed to set full as well. It's like a very real possibility. If I misunderstood this EP is TX, but again, I don't really think so. I don't think I was wrong if I was wrong. It's like, yeah, I mean, clearly that's the fucking problem, right? Okay. And then the other option here is that this, like, EP0 int 1 buff thing is maybe a little confused. Like, maybe we want to set this, like, buff status thing. For everyone? Where's this, like, SIE control shit, right? So, for every 2 buffers completed, for every 1 buffer completed, NAC, when it sends a NAC, that's kind of interesting. This guy, we want single buffered. Yeah, that makes sense. Nah. Nothing is there just jumping out at me as, like, fucking wrong. I mean, the thing, it has to be that this is not right. It has to be. Let's double check addresses, I guess. So this should be at 80 byte or hex 80 offset from buff control. And is that true? Is that true? So where are these fucking addresses defined again in here? Here we go. So addresses 0 to 0xFF are used for control registers containing configuration data. I guess we never set EP0 control. Oh, because it doesn't exist. True. But we have buffer control at 0x80. Okay. So base plus 0x80 seems reasonable. And then the control register. I guess we never set enable. There is no endpoint control register. Oh, this is control. My bad. Buffer control. Buffer control register contains information about the state of data buffers at the endpoint. It is shared between processor and controller. The endpoint is configured to be single buffered. Only the first half bits of the buffer are used. If double buffering, buffer select starts at buffer 0. From then on, buffer select flips between buffer 0 and 1. We're not double buffering. Okay. For host interrupt and isochronous packets on this thing, a buffer full bit will be set on completion even if the transfer was not successful. Blah, blah, blah. Okay, yeah. Nothing here is jumping out. Can we breakpoint here and just double check that, like, we did set the stuff that we want to set, that it, like, applied? No? Oh, maybe? Okay. So we're at 841, which is not here. That's fucking weird. Right, that's weird. That the set address call is just not going through? I guess we were technically responding before as well. That might be causing problems here. I'd be interested to try this. That's maybe kind of interesting. Maybe they call get descriptor before set address. Restart. Run. Okay. So this is here. P request 6. So he's actually calling with get descriptor first before setting the address. Okay. P request get descriptor again. So maybe that's our problem, is that we're just responding to the wrong fucking thing. Yeah, okay, hold on. Let's try going to 6 here and trying to respond. You might be in some sort of like fallback case on the host. Yeah, that wouldn't shock me. Would not surprise me. So let's say that this guy's calling get descriptor. Let's see if we can get a valid response. Right, let's just do that. So on get descriptor, what are we supposed to answer? From spec? Presumably we're just supposed to look at the descriptor type and index. Okay. So this is in W value, which is just value. Okay, so on get descriptor, I think it's saying device, right? Is what we're usually saying here. Yeah, device. So we're seeing get descriptor index. Why is value not in here? Descriptor and type index 0 or language ID. Oh, here it's he's just sure. He's just interpreting it correctly. So we're like, if we see 1, I guess we do something very similar here, right? Where we set the stuff that we're trying to send, but now we also set the transfer length to be the length of the thing that they requested, right? So that would be in here, they define that as W length, right? Otherwise we breakpoint. Okay. And then here we actually have to put the stuff that we want in there, right? So USP dpram dot ep0 buff is equal to descriptor or something, right? And I guess like USB descriptor. And that means we need to define the device descriptor. Like this is like USB device descriptor. And then this is going to be like std mem bytes as slice. As bytes. I guess this is kind of more like a mem copy, right? So kind of like this, I guess. And then we have like USB device descriptor is going to be like device descriptor. And we have to define this thing, which should be that other thing. Surely this is like the device descriptor, right? Is this 64 bytes? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. No. Okay. Oh, but I guess maybe that's like a maximum? Because I'm pretty sure, like, descriptor is supposed to respond with, like, device. Like, is that some device descriptor? Yeah, that's the thing. Which is 18 bytes. So yeah, we copy paste this. Okay. Which means that now we should be able to be like length is 18. I guess we copy paste the whole thing and just kind of figure out what's supposed to go in here. Right. Length 18. Descriptor type. This is the type of the descriptor they asked for. BCD USB. 210H. Sure. Class. Let's just set zeros here. I just want to see if like this will show as something cool. Maximum packet size for endpoint 0 is 64 probably. Vendor ID. Let's do 134. Product ID also, maybe 5678. BCD device. Device release number. So like 100. Protocol. Did I miss that one? Is because I didn't know what I wanted. Protocol code. These codes are qualified by the value of these. If field supports class. I'm just going to write 0. Manufacturer. I don't know. Index. Oh. So we don't have string tables yet, so that's fine. Serial number 2 and num configurations is 1. I don't know, man. Descriptor type. I guess we just write 1 here. I guess that's kind of okay. Now he's pissed because, you know, we have some pointless discards. Probably this guy needs to be a pointer. And 64 U8 is not an indexable pointer. Do I just do like this? Non-matching memcopy length, so 018. Hello? Like this? Okay, that compiles. Now the question is like, did this do something sane here? Why is this breakpointing there? Okay. So like, then we set this thing. Oh, but we never actually wrote it out, right? So we have to go like this. And then breakpoint, let's just take out this breakpoint for now. And I want to see if we get like a nice get descriptor request response. I don't know why this is happening. Let's just do this. Okay. So get descriptor device response. What does our response look like? No such file or directory. So that's interesting. I don't really know if that means that like it's working. I mean, we're clear. It seems like it's like, is it getting through these quick at least? Like, are we at least like attempting to respond? Get descriptor. He's sitting there for a while, just hanging out. And then I guess like we're timing out, right? He's taking 5 seconds and not answering, which really makes it seem like we're not answering, right? Right? It really seems like that. I wonder if it's like, maybe we have to fill out like the full requested lengths. Maybe. So we like mem set this thing with zeros, then copy in our descriptor, then like let it fucking rip. I don't know, man. Yeah, I mean, these are triggering like immediately now, which is kind of nice. Wait. Reset. Oh, wait, okay. No, this is talking to the... Oh, rerun it. Okay. Could it be that PID 0 is supposed to be 0? That you're... Yeah, it could be. I thought that this was supposed to... I think we saw that it was like always supposed to be PID 1, but... Could be wrong. Yeah, I mean, this is just like clearly timing out, right? Like we're just getting no ent. He's timing out. Oh, I'm pretty sure this is supposed to be 1. But let's double check that. So I seem to remember something about like always starting with data 1. Right, so we're like, we have data 0, data 1, PID is odd or even. And then I remember seeing something about like setup packets. The PID indicates the type of packet, and by inference, the form of the packet, error detection, blah, blah. No, that's not it. Blah, 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 blah. Data field can range from this. Yeah, because the reason I did it this way is because they, in their example, when they said like handle setup packet, they always reset PID to 1. Right? And so if this is 1, then they acknowledge the request. Oh, they do use 0. If next PID is 1, if this, then this one, right? It's this one. Yeah, it's this one. It flip-flops, they send you a data 0, you send back a data 1. Ah. But they use both buffers. I think it was in the RPI docs. But I think that like they're intentionally not using both buffers for this setup packet thing. Okay. I guess we should be looking at this rec direction as well, huh? But it seems like we're in like this case. What are they doing here? Always respond with PID 1 on get device descriptor. And they are calling start transfer with the device descriptor size, which is 18, and the content. Yeah, I mean, it really feels like that's what we should be sending. I wonder if there's like some bullshit somewhere. I guess maybe this was 18, right? So it really makes it seem like we're just not sending anything. I wonder if there's like some like thing we're supposed to do that like enables transfers at all. 5 bits, VBus, control enable. It's like in setup endpoints if they're kind of doing something tricky. This is only for non-endpoint 01, so this shouldn't matter again. And then they just like wait for configured. Oh. Oh no, this is while not configured, they wait, right? So configured starts as false and then gets set to true when we get set device configuration, right? So we do nothing except for like stuff that comes in and this interrupts. Okay. So yeah, it really doesn't seem like there should be a whole lot happening. It should just be like we wait, we do some shit. Do some shit. I mean, we are not doing this, which is kind of weird. I wonder if we're fucking up somewhere there. I would be interested. So here, but again, we're never seeing the fucking thing trigger. I'm just gonna throw a couple of breakpoints around again because I'm confused. So he's trying to get descriptor. Supposedly, we're just not answering, right? Which means that, like, something's wrong. Okay, let's go back here. Breakpoint. Literally just every fucking time, right? Let's really make sure that we understand the flow. So we start, we go P status. That's 0x1000, but he thinks that he's trying to call get descriptor on device. So I thought that's like a bus reset. Okay, now he's calling setup, right? So he's still waiting on that device thing, and it's just like he sent two things back to back. Okay, cool. So then we go in here, and we're like, request type. This is hex 80. Okay. So request type, where's that table of like the descriptor, the like get descriptor stuff? The setup packet format. Get descriptor. Right, so it's here. So that lines up here, right? We're saying hex 80, which is like the maximum bit. Cool. We're seeing request of 6, which is get descriptor. And so we should be going into here. Where we're like, where the fuck are we? We're at breakpoint at 890, right here. So we should be trying to send the response to get descriptor, I think. Value is 256. That seems bad. So this is a problem. Descriptor type and descriptor index. So I'm missing something here. Here. Okay. So W value field specifies the descriptor type in the high byte and the descriptor index in the low byte. Ah. So that's probably our mistake here. Right? We probably want the high byte here. And hopefully this behaves a little bit more sane now. No breakpoints happening now, which is interesting. We're supposed to breakpoint like way the fuck up here. I feel like the like either the breakpoint or like it's the behavior here is like really inconsistent. You know? Like what the fuck is going on here? Where like it's getting like totally fucking lost. I'm gonna unplug and replug and see if that changes anything. Okay, there we go. So P status setup, right? We go into the setup thing, boom, 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 boom. We see value of 256. So we come here. We should go into device descriptor stuff now. Cool. And then the question is does it answer now? So now we're like fairly confident that we're getting into this path correctly. So can we take out the breakpoints now? Just for a little bit and see if that changes shit? Like, oh my lord, dude, I'm losing my mind. So take out this one, this one. And do we see a valid response to get descriptor? That's all I want to see right now. Get descriptor. And he's just still fucking timing out, huh? But at least now, if I uncomment this, hopefully we should see that we're at least in this spot. I hope. No. But if I unplug replug and then hit run, does it behave differently? Yes. That's interesting. Wait. This is a fucking answer. This is what we wrote, right? Wait, that's good. We got a response. Right? We have 1, 2, 3, 4, 5, 6, 7, 8, ID vendor, ID product. That's super hype. So let's take out the breakpoint now. Just to like make sure that like things go smooth and fast. And 858. Where's that? This is on the reset. So let's get descriptor. Response. No such file or directory. Like, why is it different now, man? Reset everything. Unplug, replug maybe. And this is like stopped somewhere, so we rerun this guy. What the fuck did we do to make it answer correctly once? Because this one's a timeout. I guess, you know what? It did say that the system clock has to be running at 48 megahertz, and we're not. And I guess that could be biting us. How come one time it worked? It like had to do with the fact that we were breakpointing, I feel like. I feel like that changed the behavior somehow. Which is kind of funny. px status. Okay. Yeah, we're just not fucking triggering interrupts on like the. Oh! I fucking should px status. This is a setup request. Okay, yeah, there's something fucky going on, right? So here we can tell that like sometimes he is like making it through, and sometimes he's not. So I suspect that this is like that. It did just explicitly tell us this earlier, and then I forgot. The like, yo, your fucking clock sys needs to be running at 48 megahertz, right? The available install bits should be set. If running these, the available install bit should be set after other data in the buffer control register. Otherwise, the controller may initiate a transaction with data from a previous packet, which we are not doing. Okay, let's see if that changes anything. um should be set after other data in the buffer controller register. Otherwise, the controller may initiate a transaction from previous packet. Okay. We can just try it and see what happens. No, there's something else. There was also something about clock sys needing to be run at 48 megahertz. Greater than 48 megahertz. See this. Within the USB peripheral, certain host device controller events cross from clock USB clock to USB clock sys. Clock USB to clock sys. Many of these signals don't have appropriate synchronization mechanisms to ensure that they are correctly registered when clock sys are equal to or slower than this. Like, for example, transfer complete. Yeah, okay. So that seems likely to be related. Clocks. Clocks. Can we just run the system clock off the USB PLL? Surely, right? Yeah, so this is set to clock ref at power up, but then it's typically switched to PLL. And I believe clock sys is the one that's like for all like yeah, init clock sys here. So can we just change this? Sys control, this is at clock's base plus 3C. Here we go. So we can run this off PLL USB, we can. So we should just be able to do this. Aux source, we have PLL USB at 1. I think that's what it said. Yeah. Be interesting to see if this changes anything. Oh yeah, that's so much more fucking reliable. God damn it. This is what we get for ignoring shit. God damn it, dude. We should have just fixed it when we needed to. Okay. So now, does this reliably answer? Oops. Yeah, oops. Should have fucking listened. I'm a dumbass. Oh, yeah, look at it. Maybe not actually. Okay, hold on. Run. No. Uh, response here. So weirdly, these are still not responding the way I would expect. Also, what up this 192.193 shit? Oh! Wait, this is probably because we're answering the fucking set device request and then not changing our address. Right, so we're just not answering, and then he's, because the bus is like, there's no one fucking there. No one's talking to me. So here, does that mean that now we can look for the buff if set status buff status equals 1 breakpoint? Because this wasn't happening before, right? Is it happening now? We've got some fucking buff status, dude. We got some fucking buff status, bro. And so now we should be able to be like, set our address from before. So var address is equal to 0. On reset, we set the address back to 0. And then after we get a setup rec, for set address, we set the address to value truncated, and then we say var should set address is false, and we set here should set address to true like they did in the other thing. Then if we get a buff status and should set address, we have to set our hardware address to the thing. So here, we're like, we look for the hardware register on USB. Where? I don't see it in here. Where did they do it in the other guy? They had like USB hardware dev adder control. What is this? USB control regs base. Dev adder control is like right at the fucking top. Address the devices respond to set in set adder packet. Yeah, okay, cool. So we're just gonna be fucking lazy here. That's never bit us before. Fine. So, fine. Const adder endpoint is equal to base. Okay. So now we should just be able to be like, where the fuck we were. USB adder endpoint is equal to address. Should set address equals false. Okay. And if we breakpoint here, we should see that breakpoint hit. Okay, fine. This should be USB address. Fine. Okay. Okay. So now do we respond to their request on like another thing? Okay, reset, continue, run. Boom. Now... Oh, we probably have to initialize this to 0 when we reset. No, because on reset it should already be 0 by default, no? On reset it's 0. Okay, so that should work. So here we've set our address now. And then here, do we see him trying to talk to anyone other than the default address? No. So why does this feel different now? Okay, so we are... I guess the get descriptor response is now empty for some fucking reason, but also like immediately timing out because address 0 is no longer there or something? I'm confused. Unplug, replug, continue. I want to, god damn it, 9:15. So this is, we're breakpointing when he tries to set address. So let's not do that anymore. I think that we're confident that that's working to some extent. Okay. Reset this guy. And reset this guy. Boom. He calls some stuff. Now he's calling, okay, he's calling get descriptor on 116 after we've tried to move over. And that is responding. That's really fucking good. That's really good. Right? Yes, this is proof that we have set the address to what he's wanted and we fucking answered him. Then the question becomes like, well, nothing else is like doing anything, but does that mean we show up in LSUSB? No. No, it does not. And then here, who knows what else is happening now? If that is that repeatable, then if so, then awesome. That's a good question. Okay. So here we should see somewhere. Actually, let's reset this, then run. And then can we filter for type? Maybe not, huh? Control. Oh wait, maybe it was only working good on unplug replug? That might have been different. Unplug. Reset. Replug. No, I mean oh, then I have to run this again, my bad. Yeah, so request response, right? So here we're definitely seeing our thing again. Reset, so this is reset, run, no unplug replug, just reset it. Yeah, so the hard reset is important maybe? Because otherwise I'm not seeing this happen anymore. So it might be that on like port reset, we're not doing the right thing. Oh yeah, we're not resetting our address here. I'm a dumbass. So maybe we have to do this. Reset. Yeah, because now he's trying to talk to device 0 and we're just like not answering or something, right? Oh no, this is us again, no? Oh no, this is just zeros. Just a lot of zeros. Interesting. Oh, but here we did answer. Okay, so there's something close to working here. It feels like there's something that we're not doing quite right. But I think that we have at the very least proven that we are answering set address, and we are also answering set get device descriptor at least a little bit. There's definitely something fucky going on here. But I think that we have to call it here because we've just been going forever. But there is proof that this is working to some extent. Right? Because this is what we wrote down. Boom. So we'll take a break. We should be back probably not tomorrow, maybe the next day. And I guess we're gonna have to keep going on this because it's like we're not there. But we're a lot farther than nothing. So thanks for watching, guys. I hope this was somewhat entertaining to watch. I know there was a lot of just me being like, what the fuck is happening? But I understand that that's also sometimes a part of the appeal. Hard to tell. So if you want to keep up with this project, YouTube link in the Twitch description. We stream most days. Try to aim for like a 12:30 Pacific start time. It's 4:30 now, so like between 4 hours ago is approximately when we start. We try to go for like at least 2 hours, but it really depends on what we're working on that day. If you want this content to continue, it will end one day when I run on money. But that day can be delayed by, contributing on Patreon, YouTube, or Twitch. In return, you get the VODs that I feel like are not worth posting on YouTube because the algorithm doesn't hit for them. Or if you really want to be nice and get nothing in return, you could contribute on GitHub as well, but you don't get anything in return. So I think that's all the plugging we got to do. YouTube, peace out, and Twitch, let's find someone to raid.